Because of this quantum mechanical concept of identical particles, the wave function of two or more such identical particles has to have these additional properties, either of symmetry with respect to exchange for bosons or antisymmetry with respect to exchange for fermions. This means the wave function cannot just be a product of the wave functions of the two particles, even in the simplest cases. This new form of the wave functions has some very specific real consequences, one of which is what we call the exchange energy. In general, our calculations using these new forms of wave functions lead to additional terms in our calculations, which are called exchange terms. These exchange terms, or exchange corrections, are often quite significant, not merely being small corrections. Simply put, if we do our calculations neglecting the proper forms of the wave functions, we will get the wrong answers, if the particles have any reasonable chance that their wave functions overlap. We're now going to look at these exchange corrections, specifically now for the energy of two electrons. These exchange terms are encountered in practice most often with fermions, because charged particles interact strongly with one another. And the charged particles we deal with are mostly fermions, specifically electrons and protons. The bosons that we deal with most typically are particles like photons, which have no charge and which interact with one another very, very weakly under most normal conditions. Since their interaction is weak, the exchange correction to such interactions is also weak. It's important to note, though, that interacting bosons also have exchange terms or corrections. Unlike the Pauli exclusion principle, which is solely an effect we see with fermions, both fermions and bosons are subject to exchange corrections. So let's see how these exchange corrections emerge and how they work. Again, we're dealing with something with no good classical analog. Exchange corrections are a purely quantum mechanical phenomenon.
Suppose we have two electrons of identical spin. They will certainly have a Coulomb repulsion. And so we could write the Hamiltonian similarly to how we wrote the one for the hydrogen atom, except here that the two particles are identical, and the Coulomb potential is repulsive rather than the attraction we saw between an electron and a proton in the hydrogen atom. So our Hamiltonian we could write like this. We've got our usual kinetic energy terms, del squared R1 for electron 1, and del squared with respect to R2 for electron 2. And then we have plus E squared over 4 pi epsilon naught times the separation between the two particles. The plus corresponds to the repulsive potential. Because they are fermions, the state of the two particles is built on this kind of a form, with a minus sign in here. And here we are now dealing with the normalization. We're presuming that individually each of these wave functions here, psi a of r and psi b of r, as mathematical functions, have been normalized. And this factor 1 over root 2 ensures that therefore this entire wave function is normalized. We could also write this form of wave function in bracket form like this. So now 1 is referring to the particle and A is referring to the state. Similarly, 2 refers to particle 2 and B to another state, and so on. So formally, in notation, this ket vector here is psi A of R1, and so on. Now, note that the order of the products of the wave functions does not matter in expressions like this. It doesn't matter if we put this function before that one, as long as we keep it the same function of the same coordinate. And the same thing is true if we write things in bracket notation. Obviously, as I said, this product here is equal to this one. Note that we've kept A with R1 and B with R2 in both cases. And that follows because each of these is simply a number, of course, and multiplication of numbers is commutative. For the case of the bra-ket notation, we can similarly state that this product of kets is the same as this one. It makes no difference. Quite generally, the order of the statement of the vectors corresponding to different degrees of freedom or dynamical variables does not matter in direct product spaces. Now, for this two-electron state that we've just written down, we presume this is a good enough way of describing our state, and it certainly has the right antisymmetry with respect to exchange. We can evaluate the energy expectation value for these two particles in this state. So we take our state in bra form and ket form and our operator, our energy operator, the Hamiltonian in the middle, and we simply work this out. So, because we have two terms in the wave function, we end up with altogether 4 terms when we open everything out to form this entire expression here. So, the first 2 terms, which are actually equal to one another, have a straightforward meaning. Formally evaluating then, we have for that first term, written out here with the Hamiltonian explicit now in the middle, a set of different terms when we take this apart and multiply everything out. So we have this term here from the del squared with respect to R1 term, and this term here from the del squared with respect to R2 term, and this term here from the Coulomb repulsion energy. And we can give labels to each of these terms which have a physical meaning. We see here that this EKEA term is this one, this EKEB term is this one, and this EPEAB is this term. So this term here is really a kinetic energy term for the particle with coordinate R1, and in that case here, that particle is in state A. And this term here is the kinetic energy for a particle with coordinate R2, and that particle is in state B. And then this term here involves both particles in both states. So particle 1 in state A and particle 2 in state B. So, as we expect then, EKEA is the kinetic energy of an electron in a single particle state A. The bra here for particle 2 in both cases can simply be taken out of this term because this del squared is only with respect to the particle with coordinate R1. It doesn't act on any particles or states with coordinate R2. So we can simply take this term out here and put it at the end, and of course that's a normalized wave function by presumption here. So all we're left with is the evaluation of this integral, and that's a straightforward integral that we've seen before. As I said, this has gone to 1 because the single particle wave functions are normalized. Similarly, we could have worked out the second term, EKEB, which would simply be this integral. So there's nothing surprising here. This is what we would have thought we would get anyway. Similarly, this term here, the Coulomb potential energy from the interaction of the charge density from one electron in single particle state A and the other in single particle state B, is straightforward enough. Again, here we end up with a simple factor in here, and the product of the bra and the ket for particle 1 just gives us this term, and the product of the bra and the ket for particle 2 gives us this term here. So we're left to work out this integral, which is straightforward. And we have now worked out, therefore, in principle, all of these 3 terms, each of which we had seen before when working with something like the hydrogen atom. These are simple kinetic and potential energies, so no real surprises here. And we would get the same answers if we looked at this term. Identical terms would appear. So these 2 terms added together with a half, which we found in our original expression, are simply the sums of the kinetic energy of one particle that's in state A, the kinetic energy of another particle that's in state B, and the potential energy between those two particles. So this is the energy we might expect sort of semi-classically, the kinetic energies of the two particles and the potential energy from their interaction. But there are two more terms on the bottom line of this expression we'd written out before, in particular these two here. These are in general non-zero terms, and they give us what is sometimes called the exchange energy. Remember that this exchange energy is not from another kind of repulsion or another kind of attraction. It's another term that arises from the same Hamiltonian we've already been considering. But it's unusual in that, note it's got 1a here, but 2a over there, and 2b here, but 1b over there, and similarly a complementary set here. And this energy has got no classical analogue. Now, we note by the hermiticity of the Hamiltonian, this operator is Hermitian, so this term here and this term here are merely complex conjugates of one another. And so that exchange energy term that was the sum of those two terms can be written as this quantity plus its complex conjugate. And so, if you like, that just becomes the real part of this integral here. And finally, for the total expectation value of the energies of the two electrons in this state, we obtain not just the kinetic energy term for a particle in state A plus the kinetic energy term for a particle in state B plus the conventional energy, in this case corresponding to the repulsion of a particle in state A and another one in state B, but another term that we really have to work out. And in general, this term is not zero, and it can have a magnitude quite comparable to the other terms in the calculation.
The requirement of antisymmetry with respect to particle exchange therefore changes the energy of states involving two or more identical fermions. This phenomenon of exchange energy is very important in, for example, the states of the helium atom, where different energy spectra result for the situations of the two electron spins being aligned, known as orthohelium, or antiparallel, known as parahelium. It's important to understand that this change in energy is not caused by the magnetic interaction between spins, though that might give a small correction. It results from the exchange energy, not some additional term in the Hamiltonian itself. It's also true, of course, that exchange energy phenomena are very important in magnetism. If exchange energy is such a real phenomenon, and electrons in general are in these kinds of states that involve other electrons and that are antisymmetric with respect to exchange, why were any calculations in single electrons valid? The answer is that if two or more electrons are far apart from one another, there is negligible correction from the exchange energy.
If this function here, psi a of r, is only substantial in a region near to some point Ra, so some relatively sharply peaked function, for example, round some position Ra, then so also is this second derivative of that function. It's only substantial in that same region. Similarly, for the function psi b, if it's only significant near to some other point Rb, it's sharply peaked somehow in that region, and so also is the second derivative of that function. So if the points Ra and Rb are far enough apart that there's negligible overlap of these two wave functions, then this product here is approximately equal to 0, and so is this one, because this function doesn't really overlap with that one, and similarly this function doesn't really overlap with that one. Similarly, for such negligible overlap, regardless of the form of the potential energy between the two particles, this integral would similarly come to 0. if everywhere this function of R1 is finite, this one is 0 and vice versa, because they're peaked around different coordinates, then this will come out to 0, and we'll get the same effect again from the product of these two. So that's simply because these functions do not overlap. Hence, there is only a contribution to the exchange energy if the individual particle wave functions actually overlap.
This argument about exchange energy being negligible if the wave functions of the two electrons do not overlap is unchanged if we add other potentials into the Hamiltonians for the individual particles, such as a confining box or a proton to give an electrostatic potential to form a hydrogen atom. Without any significant exchange energy, the problem essentially separates again into ones that are apparently for single electrons or particles, and our previous calculations, for hydrogen for example, are completely valid for energies and wave functions.